But of course, we understand that if we come up with a theory, including them, the point of that theory would be to unify gravity with the other forces, with quantum mechanics, particle physics, and of course we expect the outcomes that are already known in those fields to come out of this theory. We cannot just ignore things that are already known, right? But extra dimensions may strike you as an artifice. Our inability to probe distances smaller than a billionth of a meter permits not only extra tiny dimensions, but all manner of whimsical possibilities as well. Even a microscopic civilization populated by even tinier green people. While the former certainly seems more rationally motivated than the latter, the act of postulating either of these experimentally untested and at present untestable possibilities might seem equally arbitrary. So at least the extra dimensions are very tiny. And so the point is that, well, these extra dimensions are so tiny we can't possibly probe them experimentally, but also that means that they are not disproved either. It would be a problem if you said something as part of your theory and that could not be, and that goes against something that is experimentally shown. But if you hypothesize something that cannot be experimentally probed at all because of our current state of technology, then at least it's not disproved, okay? Such was the case until string theory. Here is a theory that resolves the central dilemma confronting contemporary physics, the incompatibility between quantum mechanics and general relativity, and that unifies our understanding of all of nature's fundamental material constituents and forces. But to accomplish these feats, it turns out that string theory requires that the universe have extra space dimensions. So string theory, it's not just optional in string theory to have these extra spatial dimensions, it's required. So, hopefully the people who, want to support string theory, even though it's not testable, which is fine, I guess, likes the fact that it has these extra spatial dimensions, because those are a requirement here, okay? So one of the main insights of quantum mechanics is that our predictive power is fundamentally limited to asserting that such and such outcome will occur with such and such probability. So he's reminding us of the probabilistic nature of quantum mechanics. Although Einstein felt that this was a distasteful feature of our modern understanding, and you may agree, it certainly appears to be fact. Let's accept it. Now, we all know that probabilities are always numbers between 0 and 1. Equivalently, when expressed as percentages, probabilities are numbers between 0 and 100. So if it's a percentage, it would be a number between 0 and 100. If it's a fraction, it would be a number between 0 and 1. Physicists have found that a key signal that a quantum mechanical theory has gone haywire is that particular calculations yield probabilities that are not within this acceptable range. For instance, we mentioned earlier that a sign of the grinding incompatibility between general relativity and quantum mechanics is in a point particle framework is that calculations result in infinite probabilities, which is really bad. As we have discussed, string theory cures these infinities. So string theory with all its extra dimensions apparently will cure these infinities and these bad numbers of probabilities and will restore them to be good numbers. But what we have not yet mentioned is that a residual, somewhat more subtle problem still remains. In the early days of string theory, physicists found that certain calculations yielded negative probabilities, which are also outside of the acceptable range. So at first sight, string theory appeared to be awash in its own quantum mechanical hot water. So, sometimes general relativity and quantum mechanics in point particle, the bad thing can be both very big numbers that are infinite probabilities. That's not good either in quantum mechanics. And if you have negative probabilities, that's not good either in quantum mechanics. And if you're coming up with answers that kind of go against experimentally proven quantum mechanics stuff, then that's not good for your theory. So you have to save your theory updated, find the issues, and address those issues, okay?